Hello, everybody. I'm going to do a video recording today on power series and higher order differential equations. Screen will show my UI a little bit. I've had some funky setup happening here, and we get the fun static time and date up in the top left that will not change. So enjoy it being the middle of January. Yeah, so we are going to talk about power series and how they can be used to solve differential equations. And it's actually going to be a nice segue into solving some higher order differential equations. So pretty much what we've been doing so far is we've been doing first order differential equations. And we will continue to start with those on power series, but then we'll see a second order differential equation and we'll use power series to solve that, but then we'll learn more general sort of generic ways um, of solving higher order differential equations and even something like a fifth order or a seventh order or or something like that. Um, with this, a review of power series might be necessary if it's been a while since you've taken Calc 2, or even if it hasn't. I think a power series is certainly a little bit of a tricky topic, um, but it can be really, really simplified down, and I aim to do that here to try to make it not seem so cumbersome of a subject. So you will receive a sheet, not exactly like this, but I will give you a sort of cheat sheet of power series, of common power series. You will get that on your exam. So I'm not expecting you to like memorize some of these known power series. It certainly helps if you do, but we obviously still have to be familiar with them. So this is some common power series. There's certainly more, but these, this could be a good tool for you to sort of have maybe printed out and kept with you. Um, so with that, let's go ahead. Let's get into power series solutions. Um, we're going to see two. It'll look like two different ways. It's the same method no matter what. But the way we actually show our work, it will sort of be split into two different options. And I'll do some examples with both of them. But the biggest thing that we're going to do with power series is when we see a differential equation and we wish to solve it with power series, and I'll get into why we might want to do that later. But if we want to solve a differential equation with power series, we start off with an assumption. So we just assume that our solution is y equals summation from n equals 0 to infinity, an t to the n. You could do x to the n either way. Um, what this is doing is we're just assuming that we have basically some polynomial that our solution takes the form of some polynomial, but it might be an infinite polynomial. So it might turn into, sine, cosine, e to the x, arctangent, something like that. But what we seek to do is we seek to find all of these values of a sub n. Um, and that, of course, just keeps going on forever. So we have this a naught plus an a1t plus a2t squared, and this keeps going. This pattern keeps going. One thing I will note, don't confuse this with Taylor series where we have the n factorials in here. Those will appear, certainly, but they're not here in this because this is just a generic power series. So if we find out that our A naught and A1 and A2 end up having something like a factorial in them, wonderful, but that's not there off the get-go. So keep that in mind. So we've got this assumption, and basically what we do is we take this and we'll like find derivatives of this. And then from there, we'll plug and chug. So we just take these, this y prime, y double prime, whatever you need, and you plug and chug them into the DE. And then from there, we're going to match coefficients. So we're basically going to say, all right, I have a left side of my differential equation and a right side of my differential equation. I've plugged in these power series for y prime, y double prime. I've written it all out. And now I can look and I can say, hey, look, on the left side of this, there's a linear term, or there's a constant term. Let's start with that. So there's a constant term on the left side. And then I can look at the right side and say, hey, there's another constant term. Well, those have to match up with one another. And then I could say the term that has a t to the fourth on it on the left side has to match up with the term that has a t to the fourth on the right side. And so that's this whole matching coefficients thing. And what that allows us to do is it allows us to hopefully find a pattern for a sub n. Um, and really better put would be to, we're going to find a formula for a sub n noting a pattern that we see. And then at that point, you can usually compare your formula for a sub n to something to a power series that we already know. You don't actually have to do that. Um, there's some times where you can't, but if you can, it's always a good idea too, because that's a simpler answer. So that's good. Um, so there we go. Um, Cool. I think honestly, as with most things in math, the best way to go about this is to just start doing some examples. We're going to do a really, really simple one just to start off with. One that we actually can look at the answer to. Oh, sorry about that. My screen sharing might have switched into a wallpaper right there. Give me just a moment while I try to fix that actually. Go system settings. Yeah, give me just a second. All right, cool. We should be good there. So let's let's pop back in. So we have y prime right here, and this is just gonna be equal to y. We know the answer to this. This is just y equals e to the let's go e to the x. We'll use x's here instead of t. So y equals e to the x is our answer certainly. So we kind of know what we're looking for, but let's work this out and let's see how we can go about solving this, right? So the first thing that we're going to do is we are going to um, assume that y equals this summation from n equals 0 to infinity of a sub n x to the n, which if I felt like writing this out is a naught plus a1x plus a2x squared. I'll go one more, a3x cubed plus dot dot dot. Now, from this, we know that y prime is equal to the summation from n equals 0 to infinity of n a sub n x to the n minus 1. Now, you don't always have to do this in series form. You could totally just look at the written out term by term and just say, oh, look, it's a1 plus 2a2x plus 3a3 x squared, and so on and so forth. But sometimes it is nice to do this with, in series notation. It just kind of depends. And then again, depending on sort of how you want to do this, it might be nice, and I'll do this, you can see this as I move it, but I could move this over here to now kind of match up constant with linear, with quadratic, with cubic, which I don't have written fully there, but now we can see that pairing is happening really nicely. So that's cool. Again, this is our simple example. All I'm going to do, I'm going to copy and paste this. Let's go ahead and do that. We'll change the color to And then let's copy and paste this. Oh, copy, paste, change the color, and we'll go an equal sign because these are equal, right? Because we know that y prime is equal to y, I can take these two written out versions of them and I can set them equal to one another. And so uh, looking at this is where we start to match coefficients. And the whole name of the game is just looking at constant terms, looking at linear terms, and looking at quadratic terms, and so on and so forth. This always works if you have two polynomials equal to one another. There's no way that something in your cubic term is going to match up with something in a quadratic term. So I can look at all this and I can say, hey, look, this and actually, before I continue on, I realized I probably should have switched these around so that it looks like y prime is equal to y. That obviously doesn't really matter, but it's good formatting. So all of that. So now we have a1. I'll go ahead and underline. I'll put some squigglies into that. That has to be equal to a naught. So that's cool. And then let's do it with like dots. 2a2 times x has to be equal to a1 times x. I can get rid of the x's and I can just say, hey, 2a2 has to be equal to a1. So on and so forth. 3a3, I'll put some like vertical dashes, just trying to mix it up a little bit. 3a3 has to be equal to a2. And we just could keep going, right? I could continue on with this if I wanted to, but we'll see that we don't really need to. So let's take these and let's go ahead and write down sort of what happens. Right? Let's write down all these things that are equal to one another. So we have this up at the top. As we said, a1 is equal to a naught. So let's write that. We'll go a1 is equal to a naught. And then we have 2a2 is equal to a1. And then we have 3a3 is equal to a2. And we'll go ahead and stop right there. So now a1 equals a naught. Wonderful. I don't know what a naught is, but I do know that a1 is written in terms of it. The second equation, though, I could say a2 is equal to a1 over 2, which I'll actually note, since a naught is equal to a1, this is just a naught over 2. This third equation, again, we can rewrite it as a3 equals a2 over 3. But remember, A2, we actually have a definition for right here, right? So A2 is A naught over 2, but then there's a 3 right there as well that we have prior. What I'll actually note is that this happens to look like A naught over 3 factorial. And we'll go one more equation here. I don't have it written up at the top here, but we could imagine the next term on this left side would be 4a4x cubed. So 4a4 has to equal a3, which tells me that a4 is equal to a3 over 4. But we already have a definition for a3. It's a naught over 3 factorial. It's just being divided by another 4. Which then turns this into a naught over 4 factorial. So we're seeing a pattern here. Of course, up here, this 2, I can just change that to 2 factorial because they are the same thing. And now I see a fun little pattern here. And that's cool. So what we're actually seeing is that, and actually this could be good. Let's go ahead and write out a1 equals a naught over 1 factorial. I, of course, don't need the 1 factorial, but it helps see the pattern. We're writing everything in terms of A naught, and this helps us find a formula for A sub n. A sub n, this is certainly just a guess. A sub n is going to have this format of A naught divided by n factorial. And at this point, we're pretty much done with the problem. We sort of just have to go back and we have to say, all right, let's look at what we started with, right? So we started with this assumption that y took this format. And what I am going to do, I don't have to do this both ways, but I want to show you this both ways. So let's copy and paste that. And let's do it like this. Let's color code. So I could do this in the blue or I could do this in the green. If we start with the blue, which I personally think is easier, we have a formula for A sub n. And since we have a formula for A sub n, I can just plug that right in. So we have A naught over n factorial x to the n. I can do some rewriting here. That A naught is a constant, and now I have the summation of x to the n over n factorial. And for those that are familiar with their power series, this series right here is exactly equal to e to the x. And so right here, we have a formula for y. It's just a naught e to the x. And if we want to be real fun with this, we could just change the name of a naught to c. And now this gives us our final answer, where we have c e to the x. And this is exactly what we found by guessing, right? I guess I probably should have done this in the beginning, but we do, of course, have a constant here, right? So y equals c e to the x, and that is the full solution right there. Um, just by matching coefficients, we found that pattern for a sub n, and that's awesome. The other thing that you could do, and sometimes this is helpful, is you could write this out term by term, and I can just sort of brute force go in here and I can say, well, a naught is a naught. I don't know what it is otherwise. A1 we found was a naught. A2 was a naught over 2 factorial. A3 was a naught over 3 factorial. This is just me going back through these old definitions that we had, right? I can put the dot, 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 and now I can look at this and I can say, hey, look, I can factor out an a naught, and now I get 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, so on and so forth. And of course, this is a naught e to the x. Rewrite it as c e to the x if you feel like it. I think the benefits to this right side are that it makes it a little bit easier to see each term written out, whereas in series notation, you can't do that. But what I do think can get a little annoying with writing it out term by term, one, it takes more writing, but two, it can sometimes be a lot harder to identify the pattern. Of course, when we get down to this step right here, this is a really simple power series. But if you had something with really weird coefficients, if it looked all funky, it might be hard to identify what it is. Versus if you had it written in a format like a series, you might be better able um, to compare this to a known power series. So they both have their benefits. I've done it kind of both ways here, but we'll do more problems in different ways. So sweet. Let's go ahead and do another example. This example is actually quite tricky. It requires some creativity. Certainly looks pretty simple. 3x squared y. So y prime is equal to 3x squared y. I know the answer to this off the top of my head. If you want to, you can pause the video right now and sort of ponder, try to guess what an answer to this would look like. But otherwise, we'll go through and we'll do it. I have done this problem actually both sort of, I don't like calling them methods, but I've done this with writing the series in series notation as well as writing it out term by term. And this is one of the few examples where I actually think it's easier to write this out term by term. So we're going to do that. So we're going to let y equal a naught plus a1x plus a2x squared plus a3x cubed, and so on and so forth. That means that y prime is a1. I'll write it this way. Let's go a1 plus 2a2x plus 3a3x squared plus 4a4x cubed plus dot dot dot. And then I'll move this so that everything matches up and lines up really nicely. Now I have these written down, and that's great. Just for clarity of work, um, let's note this: 3x squared multiplied by y is just me taking this up here and just adding a 3 to every term and then increasing the power of x by 2 because I'm just multiplying by 3x squared. So this gives me 3a naught x squared plus 3a1 x cubed plus 3a2 x to the fourth plus 3a3 x to the fifth, and that keeps going. So change the color of that, make that look better. Cool. So we have a bunch of great info here, and we see our differential equation. And in fact, we have y prime written out. We wrote out 3x squared y. We have each of those right here. I could just set those equal to one another. So let's go ahead and do that. We'll copy and paste this. And I am actually going to make this a bit smaller. So we have that. Let's copy and paste this. Make it a bit smaller. Change that color. We'll go white. I could stand to be just a little bit bigger. There we go. Sweet. So we have this. This is awesome. What are some things that we can initially identify from here? Of course, we want to do some matching of coefficients. I look over here on the right side. I see that I start with x squared. I then have x cubed, x to the fourth. But let's go back. I start with x squared. There are no constant or linear terms on the right side. Because this is an equation and I am setting two polynomials equal to one another, if there's no constant or linear term on the right side, I cannot have a constant or a linear term on the left side. And so what this actually tells me is that a1, excuse me, is equal to 0 and a2 is equal to 0, right? And from here, a lot of really, really interesting stuff happens. What I'm going to do real quick is I am going to copy down this equation again one more time, just so that I can write it in a different way and have it look nice. Um, and in fact, I'm going to actually do a handful of stuff here. So this left side is what I'm kind of moving around. I'm going to deal with that. We already know that a1 and a2 are 0, so these terms just gone. They go away. I'm just going to erase them. So now I have this right here, but I'm actually going to write out more terms of this. So I'm going to just sort of follow the pattern quite a bit more. This step right here is not something that you would know to do while you're working while you're working this problem out. Um, I actually, as I was doing this problem, I did not know that I had to do this. I sort of figured it out as I was messing around with things. So certainly a lot of trial and error, some curiosity um, at play. As you can see, I'm just going to match up terms. Again, with the dot, 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 I'm going to line things up. I see this pattern is I always have that 3. I have a4 x to the 6th, 3a5 x to the 7th, plus 3a6 x to the 8th, excuse me, not 9, plus dot, dot, dot. Cool. So we have this written out. Same thing, right? Same thing as up here. I'm just rewriting it in a different format, and I got rid of these first two terms. So looking at this, we are going to notice this pattern. It's sort of a waterfall effect. So we know that A1 and A2 are 0. Let's just start with A1. So if A1 is equal to 0, just the first thing that pops into my head is that that term goes away. It's gone because A1 is 0. So I don't have that term. But now what I see is that if that term is 0, if that term goes away, then this term has to go away because these two polynomials are equal to one another and there's no cubic on the bottom one. So there cannot be a cubic on the top. So I'm going to go up here and I'm going to cross that out. And the reason that that is crossed out is because A4 is equal to 0. And now I go, well, okay, wait a minute. If A4 is equal to 0, well, then look right there. That term is 0. So this is crossed out. But guess what? If that term is 0, then the corresponding x to the 6th term in the top has to be equal to 0. That has to cross out. So I go up right here and I cross this out. But the reason that that is crossed out is because A7 is 0. So if A7 is 0, I have to go further to the next term, which I would then cross out again. I can't show that. I didn't write it. But that next term, as you can probably see, A4, A5, A6, it has an A7 in it. That goes away. This pattern will continue forever, where this is going to eliminate um, a lot of these terms. It's actually I could exactly tell you it's going to eliminate the cubic. It's going to eliminate the 6th, the x to the 6th term. It's going to eliminate the x to the 9th term. It's going to eliminate x to the 12th, x to the 15th. All these powers of 3, all these multiples of 3, not powers, excuse me. So all these multiples of 3, it's going to eliminate them. And that's a cool pattern that we're noticing. And I can do all this again. This is going to start to look a little ugly here, but A2 is 0, right? If A2 is 0, then this term right here, gone. This term with the x to the 4th, that goes to 0, which again makes this term go to 0. But if that term's 0, that means A5 is 0. So this term over here goes to 0. But if that term is 0, then this term above it is 0. But if that term is 0, so on and so forth. This pattern just keeps going. Now I'm going to take all this. I'm going to copy and paste it. We'll go to a new slide actually, and I'm going to get rid of a lot of this sort of fluff. Get rid of these arrows, really. Cool. So we have all these things crossed out. And what's nice about all this is that it really, really, really simplifies what we have to look at. In fact, all that I have to look at is just the squared 5th, 8th, 11th, 14th, all of those terms, right? Um, erase what we don't need. And now I see some really fun things. Right here we have really, really clean matching. I have 3A3 is equal to 3A naught. I have 6A6 is equal to 3A3. I have 9A9 is equal to 3A6. And this pattern would continue. And I'm going to identify this pattern. At this stage, we're right back where we were on the previous problem where I am just going to write out 3A3 equals, and you know what? We're going to do this on a new slide. I don't want to squeeze that into the bottom there. So we have that. Writing out our equations, 3A3 is equal to 3A naught. Of course, that just tells me that A3 is equal to A naught. I have 6A6 is equal to 3A3, which tells me that A6 is equal to A3 over 2, but A3 is equal to A naught. The last one that I have, 9A9 is equal to 3A6, which tells me that A9 is equal to A6 over 3, but A6 is A naught over 2. And again, we see the same factorial pattern where I could put a dot, dot, dot here and I could say, you know what? AN is going to be equal to, you know what? I'm looking at this and I'm realizing I don't know that I want to bother with writing out a formula for a sub n. This would be nice if I was going to input this back into the summation format that I'm writing down here in the bottom right. But we never started with that in the first place. Now, you're certainly allowed to, but I've never started with this, so I'm not going to bother with this. Let's not do this. There certainly is a pattern, and the pattern is pretty easy to identify. It's just factorials. But let's go ahead and write this out term for term. So we have y equals a naught is a naught, a1 is 0, a2 is 0, a3 is just a naught. And you know what? Again, let's go to a new slide. Let's refresh ourselves. We had kind of backtracking just a step here. This was our original guess for y. We started off by guessing this. We had that. A naught is A naught. A1 is 0. A2 was 0. We already went through all that. A3 was A naught. A4 was 0. A5 was 0. A6 was 1/2. Or, excuse me, it was an A naught over 2 factorial we wrote. Of course, all these zeros, let's get rid of them. I just have A naught plus A naught x cubed plus A naught over 2 factorial x to the 6th. Had I continued writing this out, we could include that x to the 9th term, which was that A naught over 3 factorial. For good measure, we could go A naught over 4 factorial x to the 12th. And now we get some really, really fun stuff happening here. I'm going to do two things at once. I'm going to factor out an A naught, and I am going to rewrite some of these cubes. So we have x cubed, and we'll just put that in parentheses. X to the 6th, I'm going to write it as x cubed squared. X to the 9th, I'm going to write it as x cubed cubed. And this x to the 12th, I'm going to write it as x cubed to the 4th. And that, with a keen eye, can see that this looks an awful lot I'm kind of covering it just to make a point. That looks an awful lot like e to the x. It's just the only difference is instead of an x in there, there's an x cubed. So this is just e to the x cubed. And of course, if we feel like it, change that a naught to a c. Little bit ugly, little bit of creativity happening there. I thought this whole pattern here was kind of fun, right? This sort of zigzag up and down, everything getting set equal to 0. But that's a fun problem, and we get a nice clean answer from this. So there we go. Sweet. All right, I'm gonna do another example, and this will be a good bridge. Actually, after this example, we're going to get into higher order differential equations as a sort of general method. But here we're going to do what is our first sort of real second order differential equation solved other than just guessing. Cool. So we have y double prime plus 4y equals 0. You certainly could, again, if you want to pause the video and you want to guess, you're welcome to, but you certainly could rearrange this a little bit to put it into a format that might make it easier for you to guess what our answers multiple are. Um, and if you want to pause the video and do that, you're welcome to. So same pattern. We're going to start off by assuming a power series. And what I'm actually going to do here, sort of just to show you another flavor of how to show your work, is we're not going to write this out term by term. We're going to do this in summation notation. I think that this is important to see, although I think most of you will, if history serves or repeats itself, most of you I think will prefer the term by term. I as a person, as a mathematician, prefer the series notation. That's just my preference. But I do think that this is important to show you because it does refresh us on some fun things that happen with power series, like re-indexing. So let's go ahead and continue taking some derivatives of this. I'll have n a sub n x to the n minus 1, and then y double prime is equal to n times n minus 1, a sub n x to the n minus 2. Just doing some power series or power rule there, some derivatives. So that's good. Now, before we get too eager trying to jump into plugging these into the differential equation that we have, I want to make a note of something. Again, this is not necessarily something that you would know to do, but it's something that if you were to notice it, you could be like, oh, I should maybe deal with that first before jumping into the deep end. So I look at this series down here, and actually also this one right here. I look at this series down here, though, and I say, you know what? What is the first term of this thing? I start with n equals 0. What if I were to write this out term by term? And quite quickly, we notice if n is equal to 0, when I plug that in right there, this whole thing goes away to 0. And so what I could do is I could totally just here. I'll be fun with this. I'm going to copy this. I'm going to paste it. I'm going to do this. It's right there. We'll put it in green. I could just copy this down, but instead of starting at n equals 0, I can erase that and say I can just start at n equals 1. Because if I were to start at n equals 0, it just yields 0 for the whole term. So I don't need to start with it. I can just start at n equals 1 instead, right? And then I notice a fun thing. If I were to start at n equals 1 and I plug that in right here, this term right here, n minus 1, just 1 minus 1, that's 0. So the same thing happens again. Starting at n equals 1, it's sort of redundant It's like me telling you, oh yeah, the first term in this series is 0. No, just start at the next term after that. So what I'm actually going to do is, again, I'm just going to erase this, and I'm just going to start it at 2. Now, if you're wondering, like, okay, wait, does this happen again? Well, take a look. If I plug in 2, that's good. I plug in 2 right there. I have like 2 times a 1 times a2 x to the 0. X to the 0 is just 1. There's nothing bad there, right? In fact, if you actually just write that out, you get 2a sub 2. That's that whole first term now, which is great. So we are looking at this, thinking about it as sort of a redundancy and just changing our starting value of n. I want to make this very clear. This is not reindexing. Reindexing is a different thing that I will do in a moment, but this is not reindexing. Okay. Um, if you care, I'll go ahead and even just do this in like gray so it's not as like pertinent to the work. You could do the same thing here. I could start this at n equals 1 because the first term starting at n equals 0 is just 0. So that's nice. We don't need any of this for the problem at hand because there's no y prime in our problem, but I just feel like I should note that. Um, so we have that. So that's great. Now, I look up here and I go, okay, in some capacity, I'm going to have a y double prime and a y sort of intermingling with one another. You could envision taking this term and even subtracting it over to the other side. And now it's like, okay, I'm setting y double prime and a y equal to one another. My power series for y has two issues with it. It starts at n equals 0. Let me back up. It's not issues with it, but my power series for y has two things to note. It starts at n equals 0, and it has an x to the n in it. While my power series for y double prime starts at n equals 2 and has an x to the n minus 2. My point being, this n equals 0 does not match this n equals 2, and this x to the n does not match this x to the n minus 2. So we should remedy that. And luckily, we can do a little thing called reindexing. What reindexing does is it basically just changes the value of n. If you wanted to, you could rewrite it as m or another letter. So you could say something like m is equal to n minus 2 or something like that, where you're basically saying, hey, instead of starting my counting from 2, let's start it at 0, but I need to shift things accordingly. And the way I like to think about this is, what's the first term in the green? Well, when I plug in at 2 for n, I get a 2 times a 1 times an a2 times an x to the 0. I need to have those same things appear regardless of what I choose down here at the bottom in the orange where I started n equals 0. I could start this from n equals 10, but I need to make sure that my first term looks like 2 times 1 times a2 times x to the 0. So let's take a look at this. If I have n equals 0 here, what if I put n plus 2 times n plus 1 times a sub n plus 2 times x to the n? Now I look at this and I go, okay, if I plug in 0 for all these 4 instances of n, I get 2 times 1 times a2 times x to the 0, which is exactly what I get if I plug in 2 into each of these. I get 2 times 1 times a2 times x to the 0. So I have successfully reindexed now, which is really helpful. And you don't know why it would have been an issue yet. We'll see it in a second. But now I look at these n equals 0s and they match, and that makes me happy. And then I look at these x to the n's and they match, and that also makes me happy. So reindexing has sort of saved the day. Let's go ahead now. Let's take our differential equation. We'll copy paste it. We'll write our power series out for each of these things. So for y double prime, we have n equals 0, n plus 2, n plus 1, a sub n plus 2, x to the n. Then for the 4y, we have 4, n equals 0, a sub n, x to the n. And all this is set equal to 0. I can do a little bit of combining here. I have two power series that both start from the same summation. And because they start from the same summation, I am allowed to combine these into a single sum. If these were not the same summation, you could not do that. Now you might see that's why we re-indexed before, because I was looking ahead and I said I want to be able to combine these into just one power series. And when I do this, I of course just have n plus 2 times n plus 1 times a sub n plus 2 x to the n plus 4a sub n x to the n equals 0. But now look at this. I have an x to the n in common between the two terms that are inside those brackets. So I can factor that out. And oh boy, it's a good thing that those were both x to the n, as opposed to one of them being x to the n and one of them being x to the n minus 2. Because if they did not match one another, I could not have done that factoring. Again, there's your reason why we did the re-indexing. So we have that. This is wonderful. We've got a nice, clean equation here in the brackets. We have a power series where that entire power series is equal to 0. If that power series is equal to 0, every single coefficient, every single term of that power series must be 0. So this right here is equal to 0. I'll go ahead and just box that. Great. What we can see here is this gives me a relationship between a sub n plus 2 and a sub n. So let's go ahead and take this onto a new slide. We'll paste it. And yeah, that's equal to 0. And I'll just solve this for a sub n plus 2. We'll have a negative 4 a sub n times n plus 2 times n plus 1. So what we can see here, this is actually what's called a recursive relationship. If you chose a value of n to be like 0, then this tells you a sub 2 is equal to something with an a sub 0 in it with some other coefficients and whatnot. So a2 is dependent on a0. But then what if I did like a4? Or I'm sorry, what if I chose n to be 2? Now over here I have a4, but then if n is 2, I have a2 on the other side. So a4 is written in terms of a2, and this just keeps going. Basically, all these coefficients depend on one another, right? So that's sort of a recurrence or a recurrence relation or a recursive relationship, something like that. One optional thing here, you don't have to do this, but I like to do it. I think it's helpful. Is I'm actually going to shift this. This is basically me undoing the re-indexing that I did before. And again, you don't have to, but I think that it's nice to be able to rewrite this in terms of a sub n equals something else. All I'm going to do here is I'm going to take all of these n's here, and I'm just going to shift them down by 2. So instead of n plus 2, I just have an n. Instead of an n plus 1, I have an n minus 1. Instead of the negative 4 is there, but instead of a sub n, I have a sub n minus 2. And I'm going to box this. This I really like because I have a formula for a sub n, and it makes it very clear to me that it is dependent on whatever the coefficient was 2 before it, right? So two older coefficients. So there we go. Now, you might be able to see this pattern, but I'll say it a little bit, I'll say it explicitly here because we're doing a video. The even values of n all are connected to one another. And the odd values of n are all connected to one another, but they don't intermingle with one another. If you put 7 for n, then you have 7 minus 2 equals 5 right here. So a7 depends on a5. But then a5 is dependent on a3. But then a3 is dependent on a1. And you notice evens never come into play there. You do the same thing. A10 is equal to something with a8 in it. But then a8 has an a6 in it. A6 has an a4 in it. A4 has a2. A2 has a 0, right? So all these evens are together and all these odds are together, but they're not connected. What this tells me to do is it tells me to consider this formula in 2 different scenarios where n is even and where n is odd. So we're going to take this and we're going to go just even n. And we're going to write out n equals 2, n equals 4, and n equals 6. And we should be able to see a good fun pattern emerge. So if n equals 2, I just take this top equation. I should have left it boxed. Let's take this top boxed equation, and I'm just going to plug in 2 for n. I'm just going to plug that in everywhere. So I have a2 equals negative 4 a naught over 2 times 1, which I can simplify. I am actually not going to simplify this yet. You might want to do like, oh, 4 divided by 2 is 2, and then just be on your way. I'm not going to do it that way, and you'll see why in a moment. Let's go down to n equals 4. I have a4 is equal to negative 4 a2 times 4 times 3, which is good. A6 is equal to negative 4 a4 times 6 times 5. Again, just plugging in the different values of n into this top formula up here, the boxed formula. Cool. Now let's look at the a4 equations. We're gonna look right here. I have a formula for a2. A2 is equal to this. So I'm going to take this and I'm going to plug it in right in there. So I will end up having the first negative 4. Then I have the negative 4 that comes from A2. So that matches with that. And now I'm going to have this, so I'm going to bring it in next to it. I have that negative 4, negative 4. And then I have my A naught. And then I have my 4 times 3 times 2 times 1. And this might be easy. You can see this right here is exactly right there. That's just the A2. Let's do this one more time, but down on the A6. I have a negative 4, but now I have a 4. You know what might be nice, actually? Let's copy and paste and go right there. Again, right there is a 4, and then the other stuff over here is just the other terms that are up there. A little bit weird, but we're seeing a pattern evolve, right? If I look down here at the A6, I think it's pretty clear to see that I have three negative signs. I also have three fours. I have an A naught, and I have a 6 factorial. Then in the A4, I have two negative ones. I have two fours. I have an A naught, and I have a 4 factorial. Again, very, very fun, nice pattern here. And this is why I didn't rewrite A2. I am going to rewrite it now as a single -1, a single 4 times an A naught over 2 factorial. And we've got a wonderful pattern here. This pattern right here, I can write this in terms of n, and then some fun stuff happens. So I'll kind of switch back and forth between two slides, but um, I'll go ahead and just write this out first. Um, just to start, if we look a sub n, it has an n factorial on the bottom. Yep. If n was 6, we have a 6 factorial. If n is 4, we have a 4 factorial. If n is 2, we have a 2 factorial. Then what's pretty easy is I look at this n equals 6, and I see a 3 and a 3, and I go, oh, that's just half of n. I see the n equals 4, I have a 2 and a 2. Yep, that's half of n. I see n equals 2, I have a 1 and a 1. Yep, that's half of n. So that's where these n over 2's come from. And that's great. Great. Now, what we have here, and what I really should be noting, is this is only true for even values of n. And there's a clever trick that I can do to change this formula so that it automatically works for any value of n. This is kind of like reindexing, but what I'm going to do is I'm going to replace n with 2n. And when I do that, I get the following. I get a nice formula right there. And we can look at this and say, all right, well, let's look at the blue. And let's say, what if n was 1? Well, if n is 1, then I have a2 is equal to, you can do it, plug in 1 into here, and you get something. And that gives me a value for a2. I honestly I don't even care about this over here. Let's just look right here. If I plug in 1 for n, I have a value for a2. If I plug in 2 for n, I have a value for a4. If I plug in 3 for n, I have a value for a6. So this formula right here, when I choose n to be 1, 2, 3, 4, 5, 6, 7, 8, 9, it only gives me a sub 2, a sub 4, a sub 6. It only gives me the even ones. And that's nice. And you can match it up that this does give you the same thing as this appropriately, right? As long as up here in the white, you only use even values of n, it works. So again, I don't really overthink this when I'm doing it. I just say, I'm just going to replace n with 2n. And it does what you want it to do. I'm going to do one thing. This, again, is maybe not obvious, but I am going to rewrite that 4 as a 2 squared so that I have 2 to the 2n. There is reason for that. We will see that in a bit. Wonderful. We're going to take this same page right here. I am going to copy it and I am going to paste it because I'm going to do the same exact thing, but we're going to do it for just odd n. And so I'm going to change all these values here. We're going to go 3, 5, 7. Now you might wonder why I'm starting at 3 and not starting at 1. If I were to start at 1 for n, I would have a sub negative 1 up here, and that doesn't even make sense. That wasn't even in our original definition for our power series. So I'm going to start at a3, and it will be in terms of a1. We're going to see a very, very similar pattern. We have all that. Again, this is a1, a1, and now I look, I have 5 times 4 times 3 times 2, and I have 7 times 6 times 5 times 4 times 3 times 2. Honestly, you can pause the video and take a look if you want. It's all of the same exact stuff that we just did. The numbers are just all slightly changed. They're just odd instead of even. So um, there we go. So we have all this now. Now it amounts to just finding a formula, right? Um, yeah, great. You can see the same factorials, right? I don't have the times one written on all these, but that of course doesn't change anything. It's still 3 times 2 is of course still 3 factorial. 5 times 4 times 3 times 2 is still of course 5 factorial. So that's good there. But now let's try to identify our pattern here. Well, when n equals 7, I have a 7 factorial. When n equals 5, I have a 5 factorial. When n equals 3, I have a 3 factorial. So that denominator is real easy. But these numbers maybe get a little different. I have to get from a 7 to a 3. I have to get from a 5 to having 2s, and I have to get a 3 to 1s. It's actually a lot easier than you might be able to, or than you might think. If I take this value of n over here and I subtract 1 from it and then divide it by 2, then I end up with these values. And you can see that 7 minus 1 is 6, divided by 2, I get 3. 5 minus 1 is 4, divided by 2, I get 2. 3 minus 1 is 2, divide that by 2, I get 1. So we get a formula for a sub n. It's only the odd a sub n's, but I'll go ahead and write it out. We have n factorial. We have negative 1. Remember, we took that n, we subtracted 1, and we divided by 2. We took the 4, and we raised it to that same thing, and then I have a1 right there. Honestly, if I go back here, these should look nearly identical. That right there, nearly identical to what I just wrote. It's just instead of n over 2, it's an n minus 1 over 2. Comma, for odd n only. We do the same thing that we did for the even n, but instead of replacing n with 2n, I'm going to replace it with 2n plus 1. I'll show this off to the side really quickly. If I plug in a 2n plus 1 in for the n right there, I just get n. So we have negative 1 to the n, 4 to the n, a1 over 2n plus 1 factorial. Again, like I did before, for reasons unexplained as of yet, I am going to change that 4 to the n to a 2 to the 2n. Great. And actually, I'm going to do another change. I want to do it now because it'll be very in the way if I do it later. But doing it now will actually really help us. Um, I notice that that 2n does not match this 2n plus 1. So I want to make this a 2n plus 1. So what I'm going to do is I am going to multiply this equation by a 2 and divide it by a 2. But here's what's going to happen is that 2 is going to go in there to give me, so I'll have negative 1 to the n. I'll have 2 to the 2n plus 1. That's that numerator, read 2. I still have my denominator, 2n plus 1 factorial. And then this 2 right here, I'm going to just write it as a 1/2 out front of the whole thing. I promise this will make sense in a bit. I'll make sure to come back and reference this as well. Great. We have formulas. Let's box them. We have formulas here for a sub 2n plus 1 and a formula for a sub 2n. I have formulas for the even and the odd coefficients, the an's. They're both even and odd. That's nice. Why don't we go back and let's rewrite out what we had here. This was our y. Now I'm gonna just for a moment I'm gonna dip into term by term land. You don't have to do this, but this will help us see what I'm doing. This power series can be written out like this. If I just rearrange these terms a little bit, give myself a little bit more space. There we go. So basically what I'm doing is I'm splitting this up into even and odd pieces. And maybe get a little hand wavy here, but as we already said, I have a formula for all of these even coefficients, and I have a formula for all the odd coefficients. So how this actually just breaks down is this is a sub 2n x to the n plus a sub 2n plus 1 x to the, oh, and excuse me here, I have a little typo. That should be 2n on the even one. Basically, looking at here, I don't want to count every single n. I want to count every other n. So I'm just doing 2n. And the same thing goes there. I want to count every other n, but shift it up by 1 so that they're all odd instead of all even. This stuff right here can get a little hand wavy. It's actually, it's not hand wavy, but it looks hand wavy. If you have questions about this, feel free to shoot me an email. We can chat about this in more detail. I don't want to waste that time in this video. So from here, though, we can look at this and I can go, hey, I have formulas for a sub 2n and a sub 2n plus 1. So let's write them down. Let's just plug them in. I won't bother going back. I'll just write them out. So this was our a sub 2n, and then it is, of course, multiplied by the x to the 2n. And then we have, let's write that a little better, n equals 0. This, don't forget, we had that little 1/2 floating around in there. And then we had negative 1 to the n, 2 to the 2n plus 1, a 1, all divided by a 2n plus 1 factorial. Let me give myself a little bit more space here. There we go. Certainly looks a little ugly. This is going to clean up really, really nice, though. Cool. We're going to have to do just a small amount of rewriting. First things first, this 1/2 out front. Don't need it. Don't need it inside the power series. This A1, this A naught, they're also going out front. Boom. We'll start with that. I say that and then I give myself no space to bring that out front. A naught times that sum plus 1/2. I'll just write it this way instead of 1/2 times A1. I'll just write it as A1 over 2. Sum n equals 0 to infinity. Now I'm going to start going with the rest of this stuff, but I am going to do another step of simplification. I see a 2 to the 2n and an x to the 2n. I'm going to combine those so that I just have a 2x to the n. Sorry, 2x to the 2n. But I still have my negative 1 to the n, and I still have my 1 over 2n factorial, and I don't like how I've written this. Let's rewrite it. That I like. I've got the negative 1 to the n right there. I have the 2 to the 2n and the x to the 2n combined in right there. I have the 2n factorial on the bottom. The a naught came out front. That looks nice and clean. Then over here, oh, actually, I'm going to do the same thing. I have my negative 1 to the n, but I notice that I have a 2 to the 2n plus 1 and an x to the 2n plus 1. This is exactly why back here I did this fancy one right here. Again, at the time of doing this, you did not know why we needed to do this. You would have seen that you needed to do that, though, at this stage if you didn't have, if you had the 2 to the 2n and the x to the 2n plus 1, you couldn't combine them. But by having this, now they can be combined, which is nice. So we're going to have 2x to the 2n plus 1, and then 2n plus 1 factorial. Nice and clean. Now, you may not be super adept at remembering and memorizing your power series, but these two power series are very, very simple. They are just exactly cosine of, it's a 2x, not an x, because I have a 2x in there. It's just cosine of 2x and sine of 2x. And as you might expect, I'm going to call A naught C1, and I'm going to call A1 over 2 C2. Just renaming the constants, right? This is a constant. I can totally just rename it to whatever I want. So I rename it to C2. Now we have a nice solution there. And you can check this in the original differential equation. You can verify that this is a solution. And if you even wanted to, you could verify that just each of these boxes alone are a solution. So there we go. A bit long, a bit cumbersome, um, but now is a great time to sort of ask ourselves, why the heck would we do it this way? There's got to be an easier way, right? Some of you might even been like, Ryan, why do I have to do it with power series? I could have just guessed that this was an answer by looking at the differential equation. The reason that we learn this method is because there are some instances where you cannot use other methods. So for example, we've seen something like integrating factor or separation of variables. But what if I gave you a first order differential equation that was not separable and you could not write it in the form of an integrating factor? Well, you don't have a method now other than power series. So this is really nice. Can be really helpful when you're sort of in a pinch. You can use power series. Certainly not my first choice of a method, but it's like I said, helpful in a pinch. So um, I didn't have examples of this, but I do want to note it. If I gave you a differential equation that looked like this, um, this is a very tough differential equation, but um, say you had something that looked like this and you wanted to use power series on it, you would do the same stuff that we did. You would say, hey, y is my power series. Great, let's do that. You take derivatives, you get y double prime. And when you go plug in your power series format into y and y double prime, when you go plug it back into here so that you can then match coefficients, you are going to end up with a sine of x and an arctangent of x still sort of just stuck floating around in there. What you can do though is the power series for each of these, so you can write them out. So I could go all the way back. Let's go all the way back to the beginning here, where I was writing out sort of the steps of how to do a power series problem. Um, when I said plug and chug these derivatives into the DE, really what I mean by that is convert the differential equation from its current format into a new format that is just all power series. So if you have y prime, y double prime, great, plug them in. But if you have a function, an actual function like sine of x, plug it in as a power series as well, and there you go. Um, Problems like this end up getting really ugly. I mean, you could even envision something like this. If you had a power series for sine of x multiplied by a power series, that's two series multiplied by one another. That's just scary. That's just, we don't like that. So this would be a very, very, very tough problem to do with power series. But yeah, wonderful. So with all this, um, this is a good segue. Like I said in the beginning, this is a good segue from doing a first order differential equations. But now we've seen a method that works for first order differential equations, but it also works for higher order differential equations. And that leads me into looking at higher order differential equations. Um, so yeah. Um, what I always like to do to sort of start with this, with higher order differential equations, is I like to give us an easy one, and then we just sort of guess answers. If we were in class, I would actually ask people to start guessing answers, and I would see what we could come up with. And we've kind of done this before already, um, but I'll go ahead and just sort of say like, hey, let's guess, and then I'll guess myself, and I'll give us some good guesses. Um, So if we had a differential equation that we wanted to guess solutions to, we could guess for y double prime equals y. We could guess y equals e to the t, and that does work. We could guess y equals e to the negative t, and that does work. And what we have seen, we even maybe just saw this on the last power series example, is that you are totally allowed to combine these into a single solution that is just a linear combination of the two solutions you've found. Um, and this is where in class I would actually ask, I'd say, okay, I got my answers. I have two answers. That's wonderful. But why do I have two answers? And can anybody come up with another answer? Um, I have two answers because it's a second order differential equation, and that pretty much always happens. But then usually what happens in class in real time, somebody says, "Oh, wait a minute. What about hyperbolic sine?" And then somebody goes, "Oh, wait, what about hyperbolic cosine?" If you take two derivatives of these, they work in this. The second derivative of sinh is sinh. The second derivative of cosh is cosh. And so I'm looking at this and going, okay, wait a minute. How do I have four answers to a second order differential equation? It's because you don't actually have four answers. What's actually happening here is sinh and cosh can be written in terms of e to the t and e to the negative t. And so while it might look like I have four answers, it's actually that I really have two, but I could just combine these two in other ways that clean it up and make it look like new answers. I could take a linear combination of these two, and get new solutions. And we have done this a lot. This is hinting at a lot of things that we saw in linear algebra, things like linear independence. So you might ask yourself, hey, if I've got all four of these that are answers, are any of them redundant? Can I erase any of them and it doesn't change my set of answers? So we're kind of seeing some linear independence here. I could also talk about subspaces. We could talk about vector subspaces, or vector spaces and subspaces, I should say. The solutions to this differential equation, are they a subspace? Are they closed? So can I take two solutions to this, add them together, and it is still a solution? Can I take a solution of this and can I scale it by a constant and it's still a solution to this? And you can ponder those questions, and we've kind of already talked about a lot of that stuff, but those are things to think about before we really get into methods for solving higher order differential equations. Um, this slide in general, it has nothing to do really with like the methods I'm about to bring upon us, but think about these things for the next, several lectures as we learn about higher order differential equations. Think about linear independence. Think about subspaces. Think about linear combinations. All that good stuff. So, um, cool. We're going to do a very general example here. We're just going to jump right into it. I'm going to give us a second order, constant coefficient, homogeneous, autonomous differential equation. So there's no t that appears anywhere. It is homogeneous because I have all these y pieces are just sort of, they don't, actually I shouldn't say it that way. There's no t's or constants that are like floating around, right? Um, More informally put, it's set equal to zero. And there's some issues with that. We've talked about that before, but I won't go into that. But this is homogeneous. The coefficients are constant. And this is also hopefully very clearly not a separable DE. There's no way that you could separate this because I have a mixture of second derivatives and first derivatives being added together. Um, so I look at this and I go, okay, I need to solve this. How the heck do I solve this? As we always do, we guess. Let's just guess at an answer and see what happens. And what I'm going to do is I am going to note that I have derivatives of a function. I have derivatives of y being added together, and they all have to cancel out to zero, which sort of tells me that y prime, and y double prime should all be the same type of function so that when I add and subtract them together, they can cancel one another. Like very clearly, if y was a sine of t, and that means y prime is a cosine of t, there's no way those are canceling to zero because they're totally different functions. So we ask ourselves, okay, what function has derivatives that give you the same function? Exponentials. So I am going to take y equals e to the rt, and I am going to plug it in to this differential equation. And if I do this, well, I'll even note y prime is r e to the rt, y double prime is r squared e to the rt. So I end up with a r squared e to the rt plus b r e to the rt plus c e to the rt equals 0. This is me just plugging it into that differential equation in the white. And now for two reasons, I can divide e to the rt out of this. One reason is that e to the rt, because it is an exponential, it can never be 0. And the other reason is that if e to the rt was 0, that just means that I would have started with y equals 0, which is very clearly a solution to this differential equation. So it's sort of like there's no reason for it to be 0. Like I know that 0 is an answer, so I'm not going to guess some fancy form of something that is actually just 0. So we end up with this. This is a very fun equation. We know how to solve this. This is a quadratic equation. It can be solved with the quadratic formula. Um, I'll even just go ahead and write r, and I'm going to label plus and minus is negative b plus or minus the square root of b squared minus 4ac all over 2a. So we get two answers for r here. And right there, that just gives me my two answers. We guessed y equals e to the rt. We guessed this as an answer. And through plugging this into the differential equation, I got values for r. Certainly, if you had actual numbers for a, b, and c, you plug those in, and I get two different values for r. Since I have values for r, those are my answers. Done. This is basically a mixture of guessing and the verifying a solution to a differential equation. So I've sort of guessed a solution and I've said, hey, let me verify that this is a solution. But because I have an unknown in it, when I verify this, when I plug it in, it gives me the values of that unknown. And now we have our answers, which is awesome. In this case, two of them. Um, I will note this does not have to be second order. It could be third order. It could be fifth order. It could be ninth order. If it was, say, third order, you could envision that this equation down here would end up with like an r cubed down here, right? Actually, I'll even just do that. If I had y triple prime just thrown in the front there, I would just have an r cubed on that bottom left, which certainly makes this a lot harder to solve. You can't use the quadratic formula, but use some other method to factor this, right? Basically, what I'm getting at is when you plug in y equals e to the rt into this, it turns into a polynomial equation that certainly has some answers to it. The question is, how many answers does it have? I've actually said this a couple times, and it's actually technically incorrect. I've looked at this in the orange and I've said, yeah, we got two answers. But is there always two answers? No. This is a quadratic formula. There can be three different cases. If b squared minus 4ac is positive, then R is real, and we'll say distinct. There's two different R's. I'll just say like R1 and R2. Just kind of put that there. But what the heck happens if b squared minus 4ac is equal to 0? What the heck happens if b squared minus 4ac is negative? Right? These are obviously very simple algebra ideas, right? Quadratic formula, but I want to write them out. R is real, but it's repeated. And what I mean by repeated is there's only one of them. I'll say there's just R1. If b squared minus 4ac is negative, and I have a negative underneath that square root, that gives me complex R. And if you really wanted to throw this in here, I could label them as R plus minus. I know I'm really squeezing that down there in the bottom. I have R plus minus. They look like this format, A plus or minus BI. We will see that in better detail later, but I'll just note that here, and maybe if that makes sense too, it's like, all right, cool. So we have three cases, all right? What we're basically going to do is we're just going to go do three examples. We're just gonna work out these examples, and we're going to see what happens. Right. The first example, really easy. And I'm going to go ahead and write real / distinct roots. So sort of like case number one. Let's do y double prime minus 7y prime plus 10y equals 0. Now, if you want to, and I recommend doing this in the beginning, if you want to, you are totally welcome to say, hey, let's guess y equals e to the rt, and let's plug it in, and let's see what happens. What is always going to happen is it's just going to turn into this. Your y double prime turns into an r squared. Your y prime turns into an r, and your y doesn't have any r's. It's like an r squared, an r to the 1, and an r to the 0. That always happens. We generalized that here. I have no problem with you jumping right to that stage. You are totally allowed to just go boom and just make that jump. Okay. From here, I have a quadratic equation to solve. And luckily, this is easily factorable. So I get R1 is equal to 2 and R2 is equal to 5. This yields some different equations. I shouldn't say equations. This yields answers. Remember that we guessed, I didn't write it down, but we guessed that y was equal to e to the rt. So I have two answers here. Y equals e to the 2t and y equals e to the 5t. And you can check these. If you take each of these, I'll say this here, pause the video, verify that these two answers in the green, verify that they solve this differential equation. So you can take this and plug them in to that, each of them separately, and they will work. They totally work. The question is now, what can I do with these? Well, we've talked about this. We've seen this before. I'm going to write this out explicitly. Because we have a linear and homogeneous DE, we can take a linear combination of these solutions, and it is still a solution. So this gives me y of t is equal to c1 e to the 2t plus c2 e to the 5t. And we get an answer. We've talked about this a little bit, and I haven't formally done this yet, but you are not allowed to do this linear combination thing called superposition. We've used that word. You're not allowed to do that if this is not homogeneous. And you're also not allowed to do that if this differential equation is not linear. But fortunately, in this example, and many of the examples that we will do, this is linear and homogeneous. So we're good. We're allowed to do that. Great. Pretty straightforward. Let's do it again. Real repeated roots this time. So we have that. So here, y double prime plus 6y prime plus 9y equals 0. Again, jump right to this for both your sake and my sake when I'm grading these. Just jump right to there. Boom. R squared, 6r, 9. Done. You are welcome to use the quadratic formula at any moment that you want here. You are welcome to complete the square. You can factor, you can do whatever you need to do to factor this thing, to get answers for R. So it's up to you, but I will just note that this does very cleanly factor into R plus 3 squared. So I get R equals -3. So that gives me y equals e to the -3t, because again, the whole point of what we're doing here is we are guessing that y is equal to e to the rt. I want you to ponder for a moment. What feels a little weird? What feels off? We don't have a second answer, and this is a second order differential equation. And you might think, oh, well, that's okay. That's fine. No, it's not okay. Because we have a second order differential equation, we have to have another answer. And so the question becomes, really, this is a very difficult question. What the heck is my other answer? Right? What do I do? As we always do, guess. And the format for this guess is not obvious. It took mathematicians, historically, it took them a very long time to sort of come up with this and really figure this out. But we are going to, and I'll go and write this out. For our second solution, guess, let's label why one of t is down there. We're going to guess why 2 of t is equal to e to the rt. And actually, excuse me, not e to the rt, e to the -3t. We've sort of already found that piece, but I am going to multiply it by a v of t. I'll rewrite that a little bit. So we have one solution that is just an exponential, e to the -3t. But now I'm guessing, okay, well, I need another one. It probably should have an exponential in it, but maybe it's an exponential multiplied by something else. And I have no idea what that something else is, but it certainly is a function. Let's call it v of t. And now this gets really, really annoying, really ugly. Um, what I could do here is I could take this and I could, in theory, actually, this is what I should do. I should take this and I should just plug it in to there. And I work out the algebra and I see what happens. And I'm quote unquote going to do that, but I'm not going to do it for this specific example. I'm going to do it for the generic example. And the algebra here is going to get a little ugly. We're going to have a lot of A's, a lot of B's, a lot of R's, and a lot of V of T's floating around, as well as a lot of derivatives. I actually already have all this written out. I am not going to go through this super carefully in the video. I'm going to do it pretty quickly, but I will screen share these and sort of click through them, sort of swipe through them somewhat quickly. If you want to pause the video on any of it and sort of dive deeper into these derivatives that I'm taking and what's happening, be my guest. But I'm going to give us just this general overview. Okay. So I'm going to go over here, have all this written out already. So let's say we have this differential equation, right? We do the same stuff where we convert it to here, and I can solve this for r, and I get the quadratic formula. But remember, we are dealing with the case here where b squared minus 4ac is equal to 0. And so that whole square root part goes away, and all I'm left with is just negative b over 2a. So I have my single value of r right here, negative b over 2a, which then tells me that my first solution, I wrote y h1 for homogeneous because it's a homogeneous differential equation. You don't really have to do that. Doesn't really matter. But I have d e to the negative b over 2a t. I just chose to use the letter d for my constant just because. Then, just like we did before, I say, great, I have one answer, but where the heck is my other answer? So what I do is my other answer is right here. It's just what we did, where I just take the answer I had and I say, well, let's put a v of t in front of it. Now we get ugly. I say, all right, if this is my guess for my second answer, I have to plug it in not only there, but I have to plug it in there, and I have to plug it in there. So I need derivatives of this. And that's what all this work is right here. I'll even separate it out a little bit. You can pause, you can go through these derivatives. I'm basically just doing the product rule and I'm cleaning things up. Remember, I don't know what v of t is, so I have v prime written in there as its derivative. Product rule, do some factoring. Now I have to take a second derivative. I do the product rule again. I do a whole bunch of factoring, and it turns into this whole big thing. Ugly. But there you go. There's your second derivative. There you go. There's your first derivative. There you go. There's your original function. I am now going to take all three of these, and I'm going to plug them in to the three spots in the differential equation. And again, it's very ugly. So I have my differential equation. I plug in that second derivative, that first derivative, and then the original guess. And it's all there, and it's set equal to 0. And then what I do here is I factor. Actually, this next step right here, I get rid of these exponentials, divide them all out. Now I have this right here, which is actually, you can see, sort of grouped really nicely. It's A times a whole bunch of stuff, plus B times a whole bunch of stuff, plus C times a whole bunch of stuff. I just expand this out, and then I regroup it so that I expand it out, I do some canceling and some simplification, and now I group it so that I have V double prime and V with some constants out front. But what's super cool is the constant that is out front of the V is equal to 0. And you can check this on your own, but if b squared minus 4ac is equal to 0, it means that what I have highlighted is equal to 0. And you can check that. But that whole term just poof, gone. So I'm left with just av double prime is equal to 0. Av double prime is equal to 0 corresponds to v double prime is equal to 0. And this has a really neat solution. I like to explain this graphically. What function has no concavity to it? A line. So v of t is just, I wrote alpha t plus b. You can use other letters if you want, but v of t is a line, is the point. Let that sink in. That's really cool. V of t is a line. I just found v of t. So right here, boom. Put alpha t plus b right in there, and we have our second answer. I've written this out. Here's that second answer. second solution. I plugged in the alpha t plus b, and now I'm just to show you what happens. Let's expand this. Let's distribute this, and I get that. Now, per what we've done before, per superposition, you are allowed to take our original answer that we had, the second answer that we had, and I can add them together. And it is still an answer to the differential equation. But watch what happens. I have this right here added to that. It's just d plus a beta. Call that C1. And then call alpha C2. And now I have a nice, clean, final answer. I'm just combining these together. Again, I'm renaming some constants at my leisure, but there we go. I have this. And the reason that this is really nice is that looking at it in this format, I forget all this fluff that we've done for several slides. And I say, all right, this right here is my answer to the original differential equation. Well, look, there's one answer. There's a second answer. And this gives us a pattern. This tells us what to do. What we do when we have repeated roots in a differential equation, we just add a t. We just slap a t on there. And that gives us our second solution. So let's go back here. And I'll say per next slides. After I finish this video, I'm gonna take the slides that I just showed us and I'm gonna like put them right after this one right here. I'm gonna sort of merge it together. So I'll say per the next slides, y2 of t, we just say it's t e to the negative 3t. And now we have our final full answer. We just have y of t is equal to c1 e to the negative 3t plus c2 t e to the negative 3t. And we have a full solution to the differential equation with the y double prime plus 6y prime plus 9y equals 0. Generally speaking, if you had a repeated root, say that this was like, say you factored it down, say I had a higher order differential equation, it was like a fifth order, and you had like r plus 3 to the fifth, your solution would just be e to the negative 3t plus t e to the negative 3t plus t squared e to the negative 3t plus t cubed e to the negative 3t, t to the fourth. You would just keep going until you get as many solutions as you need, right? Um, and I will actually show you an example kind of like that in a little bit. But yeah, cool. So just sort of in recap, when we have distinct roots, this is like case number 1 right here. When I have my two R's, that's real easy. I just have my two R's, I just do superposition, linear combination, combine them. Great. When I have repeated roots, I take it, slap a T on it, and now that's my other solution, right? And if I had a third order and it was repeated 3 times, then I would slap a T and slap a T squared on it, and then I have my regular, my T squared, and then boom, you're good. But let's go to this third case where we have complex roots. Oop, that does not look good. All right, so we are going to do 2 examples of this. First off, we're gonna, and I'll go ahead and note this, like b is going to be 0. So what I mean by that is we're going to have y double prime plus 4y equals 0. I don't have a y prime term. That b was that coefficient on the y prime. We can go back here, right? So b is 0, so there's no y prime. That's my first example that I'm going to do here, and we will end up with complex roots. Interestingly enough, we have solved this today. We did this in power series, and we're going to do it again right here. I do the same thing that we always do. I go r squared plus, it's not 4r, it's just 4. There's no y prime, so there's no r term in there. So we have this. Don't overthink this. This isn't factorable, but I don't really care. I can just subtract 4, I can square root, and I get plus or minus 2i. So now I have two solutions. I have y equals e to the 2it and e to the negative 2it. If I wanted to, I could label this as r plus minus. I have two answers. Oh, I didn't write that very nicely. Let's write y equals. And actually, even better, let's go y2 and y1. All right. And what you would do here is we would go superposition, say per superposition. Again, all today, we're only dealing with linear homogeneous differential equations. So I'm allowed to do the superposition. Y of t equals c1 e to the 2it plus c2 e to the negative 2it is a solution. But that's a solution that has complex letters in it. I don't like that. You could technically box this and it's a right answer, but it's not something that anybody, myself included, is going to accept as an answer because it does not look real. It is real, but it does not look like it. So what we're going to do to fix this is we're going to use Euler's formula. Euler's formula states that e to the I theta, you could do e to the it, e to the ix, doesn't matter, but e to the I theta is equal to cosine of theta plus I sine of theta. And I'll also note, this isn't a different formula, but if you put a negative sign up in there, due to cosine being even and sine being an odd function, e to the negative I theta turns out to just be the same thing, but with a minus sign. So that's kind of nice. What we can do with this is we can take our our in the yellow. We can take this and we can we can change it. We can change how it looks using Euler's formula. If I remember correctly, I think I have this actually written out. There we go. So here, let's go back. So we are going to take this right here, and I'm going to I'm going to apply Euler's formula to that I've boxed, to each of the two things that I have boxed. And when I do that, it looks like this. Again, not going to go through this super carefully, but right there, you can see that sort of applied in there. You can see I have the negative signs in there. That negative sign, again, cosine is even. I did that here. Sine is odd. That negative sign comes out front, so that's nice. I have all this. I am going to group from here. I am going to group this into real pieces and imaginary pieces. And when I do that, I have a C1 plus C2 cosine of 2t. And then I have an I, and I have a C1 minus C2 sine of 2t. Actually, just for a moment here, I should have erased this in the beginning. I'm going to erase this. Don't look at it. Don't read it. Okay, we have this. What is totally allowed, although it might feel a little uncomfortable. I can rewrite C1 plus C2 as D1. That's good. I can rewrite I times C1 minus C2 as D2. You are totally allowed to do that. And the reason you're allowed to do it is kind of because of something I've never really said before, because I've never needed to. It's never really been applicable. There is nothing in a differential equation course that says that my answers cannot be complex. There's also nothing in a differential equations course that says that my constants have to be real, that they cannot be complex. So actually, I'll phrase this in a funny way. Maybe I've been tricking you this whole time, or like maybe not tricking, but like I haven't told you the full truth. Um, let's go back here. Like when we have done this, we've done this over and over right here, where I took two answers and I did a linear combination per superposition and I combined them. I have maybe implied that C1 and C2 are real numbers, but they don't have to be. They certainly are allowed to be complex. There's nothing wrong with that. So we get here, this rewriting, totally allowed. Now, if you don't like that, if that feels weird to you, here's what you're allowed to note. If you ignore all of this algebra, all of this fluff, all of this stuff, specifically speaking, if you just look right here and right there, just look in the red boxes, each of those are solutions to the original differential equation. You can verify that on your own, or you can rewind maybe about an hour into this video and look at where we solved this with power series and we got these two answers. Each of these are solutions to the differential equation. And very clearly, sine and cosine are totally different functions from one another. I could use the word linearly independent, and I wrote that down here, but we haven't fully defined that for functions, but there's some linear independence there. There's some linear algebra. Sine and cosine are completely different functions for one another, and they are both solutions to the original differential equation. So I am allowed, for the same thing, for the same thing that we've been doing all over here, where I have taken two answers and I have added them together in linear combination, I am allowed to take these two and go C1 times one of them plus C2 times the other. And I can do that with this sine and cosine. So either way you want to think about this, both are totally legitimate. It's all good. It's all good. But this is my answer right here. In fact, I'm going to copy this page. I'm going to do this now. I'm going to copy this and bring this over to my other. So we have that right there. This is it. That's boom. Here, let's box it. My constants are D1 and D2, where we usually write C1 and C2, but heck, change them. Change them to C1 and C2. Nobody cares. It's just rewriting of constants. So um, there's our answer. Done. And we got that before with power series. So we know that we've done it right. We'll do one more complex roots. Then we'll do one scary looking but fun example. And that'll be it. In this one, b is not going to be 0. So I will have a y prime term. Just like before, r squared minus 6r plus 25 equals 0. If you go through the quadratic formula and you do all of this, or if you complete the square and you solve it that way, however you do this, we get dot, 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 and you get r plus or minus is equal to 3 plus or minus 4i. So again, we have y of t is a superposition of C1e to the 3 plus 4i t plus C2e, I'm running out of space, to the 3 minus 4i t. Let me do this. There we go. split that. Great. Um, Again, like we did, right? We just did this right here. I can take this whole thing and I can continue. I can do the same thing that we did. I'm going to note something though. Something happens before I do that. If I use exponent properties, we get that, which I can then factor out in e to the 3t. And I have c1 e to the 4it plus c2 e to the negative 4it. And exactly like we did before, you know what, I really probably should just be doing this on a new slide. Let's go ahead and here, let's copy all of this. Let's go to new slide. So we have that. I'm just going to erase all this. So we have all this doing exactly what we did before. I'm going to have d1 cosine of 4t plus d2 sine of 4t. Done. There's your final answer. If you want to write it like this, you're more than welcome to. This is usually how I write my answer. It's just personal preference. Oh. Remember, the dot 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 is exactly what we did on this slide back here. It's just instead of a 2 everywhere, it's just a 4 everywhere. So same exact thing. And then we get our final answer, and I can box this. So these two examples are good. They show sort of a slight difference in this complex case. In the complex case, if you don't have that y prime in there, if b is 0, your roots will be purely imaginary. There's no real piece over here. There's no number right there. And so when it's purely imaginary and you go through and you do all the Euler's formula stuff right here, you end up with only sines and cosines. But when you have that y prime, you will always have a real part to your root. And so if you have a real and an imaginary part and you go here, this e to the 3t sort of just factors out. Now you do all the same Euler's formula stuff and you get your sines and cosines, but there's an exponential multiplied by them. So you have your exponential times a cosine and an exponential times a sine. You are more than welcome to jump from right here to the final answer. These problems are quick. I'm not expecting you to do all this Euler's formula. I have done it for you in lecture now. You can say, if you want to, you can be like, per Ryan's lecture. You are totally allowed, like, quite literally, this would be the whole problem. Give me a sec. Done. Like that's all the work that you have to show. If I give you this, you just have to show this work, including this dot dot dot. I need to see that work for like quadratic formula. I need to know that you didn't just, cheat or something and just get this. But you can literally just write out the characteristic equation. I never said that term. I'm going to define that in a moment. You can just write out this right here, do the quadratic formula or whatever, get your answer, and right from here, boom, you're done. I just said it and I realized I never said this before. This right here is called a characteristic equation. Okay. This method is called solving a differential equation with the characteristic equation. So there you go. Great. One last fun example. I'm going to call this like a combined case. So we've seen cases where our roots are real. Those real roots can be distinct or they can be repeated. We've seen two examples where we had complex roots, um, where our roots were either purely complex or a mixture of real and complex. There is nothing stopping us, though, from having a problem that has both, say, complex roots as well as some purely real roots. Super ugly. We have the fifth derivative of y minus the fourth derivative of y minus 7y triple prime minus y or minus 29y double prime minus 144y prime minus 180y equals 0. This gives us a characteristic equation that looks like this. And we, of course, would look at this and we would say, good luck factoring this. I will note there are methods to factor this, most notably the rational root theorem. And I'll say the following. Problems like what I'm showing you are fair game. I, of course, would make the numbers look a little bit cleaner, look a little bit nicer. But things like the rational root theorem, there are other methods, factoring cubics, all of that, factoring by grouping, all long division, synthetic division, all of these methods are fair game. They're things you've learned before, and they may show up in problems here. So maybe a quick refresher of rational root theorem, long division, synthetic division, factoring, cubics, some of that stuff might be needed. But per that, we have this factoring all the way down to this. And this is where you could look at this and you go, okay, I have values of r. I have r equals 5, r equals -2. Here, let's say r1, r2, r3 equals -3i, or let's do positive 3i, and then r4 is -3i. Like I have all of these, they're all mixed together. We haven't seen that before. But what do I do now? You basically just treat it independently. You treat each thing on its own and you just sort of add some plus signs in there. So what this turns into, let's go ahead, I'll copy and paste. Great. So we have all those. This is actually just super simple. Y of t equals c1 e to the 5t plus c2 e to the -2t. But don't forget that -2 was a repeated root. So I have to repeat that root with a c3t e to the -2t. So this chunk right here corresponds to that. Now, I said I would come back to this. I would hint at this. If this was cubed instead of squared, it's not. But if this was cubed, then I would add a c4 t squared e to the -2t. And if that was, instead of being cubed, if it was to the fourth, then I would add a c5 t cubed e to the -2t. You just keep adding the extra t until you have enough of those that you need. So there's that. And then we wrap this up with a c4 cosine of 3t plus a c5, I'll write it this way, sine of 3t, where both of these are corresponding to both of these. So it's just stitching together each individual part. I wonder if this actually makes more sense. I'll write it like this. Let me do this. This will look kind of fun. There you go. Final answer. Right. So if you've got these situations, these different cases combined, you just do each of them individually and then just add them together with some pluses, and you're all good. Sweet. A long video. I appreciate you sticking through to the end if you're here and you didn't just fast forward to the end. But that's a good like I said, a good segue, right? Using power series as sort of a segue from first order to higher order differential equations. But now we're seeing how to do higher order, right? And we have this characteristic equation, right? All the R stuff. What we move to next is wondering, how do I solve one of these but when it's not set equal to 0? How do I solve this if I have something else other than 0 on the right side of these differential equations? Because every single one of these examples we've done has been homogeneous. But what if it's non-homogeneous? What do we do? Right. So that's where we're moving forward to. And we've got the good building blocks of what to do here, because it actually, interestingly enough, what you do when it's non-homogeneous depends on which one of these cases you're in if it were to be non-homogeneous. I'm sorry, if it were to be homogeneous. So, yeah. Again, thanks for watching. I know it was a long video, but that'll be it. I'll go ahead and stop the video now.